After the consecutive successes of the India International Science Festivals from 2015 to 2019, the 6th India International Science Festival will be held from 22nd to 25th December 2020. Due to the corona epidemic, this year the festival will be held through virtual and online media. This is slated to be a huge platform for science communicators, scientists, doctors, researchers, and students to interact and connect with each other. Because of the increasing demand for science and technology, this year the theme of the festival has been appropriately entitled Science for Self-Reliance and Global Welfare. Here students will get a chance to explore new frontiers of science and technology, along with many other scientific thought-provoking ideas. Many eminent scientists, doctors and researchers who have contributed to human welfare in various fields of science will share their knowledge and expertise in the context of COVID-19 and other novel scientific innovations and applications of various domains of science. Realizing the significance of bringing participants face to face with scientific novelties and challenges, this theme will encompass diverse scientific domains including nanotechnology, astronomy, Ayurveda and yoga, space astronomy and astrophysics, quantum physics in medicine, ergonomics and pharmacology, environmental pollution, climate change, artificial intelligence and infectious diseases. Spearheaded by various ministries and departments and the Council of Scientific and Industrial Research, this festival invites scientific leaders, students and the general public to join in and celebrate the achievements, discoveries and innovations in science and technology and their applications for the betterment of human lives. It aims to provide ample opportunities to 9th to 12th class students to participate and get aware of the prevailing scientific endeavors in the country. This promises to be a platform to promote new ideas towards self-reliance and global welfare. We invite you to register before 15 December 2020 and be a part of this grand event and familiarize yourself with the current scientific knowledge and know-how.
Promo. Good afternoon, everyone. Thank you for joining this session of Vigyan Yatra organized by CSIR Institute of Genomics and Integrative Biology under the 6th India International Science Festival. CSIR-IGIB is one of the 38 labs of the Council of Scientific and Industrial Research, India. Our institute focuses on problems in biology through multidisciplinary approaches. Today, Director IGIB Dr. Anurag Agarwal will be delivering the welcome address, and we will be joined by the guest for the event, the Principal Scientific Advisor to the Government of India, Dr. K. Vijay Raghavan, who will deliver the keynote address. His talk will be followed by a question and answer session, so you can drop your questions in the comments on YouTube and Facebook. Following that, we will telecast a video compilation showcasing the highlights of research at IGIB. We will end the session by vote of thanks. I now invite Dr. Anurag for the welcome address.
Thank you very much, Samatha. Hello. Hi. So it's a Pleasure to meet you all on a very auspicious day as we launch one more edition of an Indian Science Festival. I do not know how many of you are aware that in our Constitution, under Article 51 AH, it's a duty of a citizen to develop scientific temper. Not just scientific temper, but humanism and a spirit for inquiry and reform. Now, these are very important words put in there by the founding fathers of India. And if you really think about it, what is scientific temper? Scientific temper is proceeding in a life by logic, a spirit of inquiry, a spirit of observation, analysis, and communication. Not necessarily always in this order. Sometimes we communicate first, we think later. But by and large, we live in a country that has recognized the importance of thought, discussion, and discourse. Now, IGIB is one of the younger institutes of India. We do not have the legendary long pedigrees pre-independence of many CSIR labs, like the National Physical Laboratory or the National Chemical Laboratory, which predate independence. IGIB started as a small unit of CSIR in 1966. Why did it start? It started because the country was dependent upon every small enzyme from outside. There was a vision in which we could use waste products and convert to useful biochemicals. And it grew like that for many years. Somewhere in the late 90s, when Professor Samir Brahmachari joined from Indian Institute of Science, he saw the opportunities of a new area of genomics. We were just starting. The Human Genome Project had started. India had unfortunately not really been that the world would be transformed in the time to come. And because of that, he wanted to start functional genomics at IGIB. He started what was called the Functional Genomics Unit. And this Functional Genomics Unit went on to expand and become larger than institute that initially formally changed to the institute in two, and I've been here for the last 13. It's been a very interesting journey when you look at IGIB. You look at the concepts that went behind the formulation of a strategy behind an institute that it intended to be about. If you look at the mission statement of an institute, you can understand what is it that we plan to do. And then, of course, you can judge, are we succeeding in doing what we plan to do? Our mission is to translate concepts developed in basic biologicals for healthcare. Now, let me pick up on a few words that will help you understand the slideshow, the videos that will come later. Concepts, basic biological research, commercially viable technologies, and healthcare. This sentence is so important. It recognizes that there is no health, there is no healthcare without basic biology. Almost everything you think of in the world of medicine today came somewhere from the world of biology. There is nothing that starts de novo in the world of medicine. And that is so important. Adults who are would be well reminded to remember that the essence of all of medical care starts from the years you subject, the years you study the basic subjects, physiology, biochemistry, anatomy, and so on. And all of those subjects derive from fundamental biology. The second important part of this is commercially viable. Now, there is a limited amount of support that can be given in the country towards pure biological research. One wishes it was more, but it's important for every institution to work upon also looking at technology development. And such technology development needs to be commercially viable to be able to be implemented in the area of healthcare, which basically means what? Somebody must want to use the science that you're doing. And how do you determine that somebody would want to use the science you're doing? By asking, if this science never got done, what would suffer? And so IGIB has divided itself into 5 43 scientists, and we have hundreds of young researchers. Our first area, that is the largest area, is genomics and molecular modelism. Now, this, as our name would suggest, is the essence of who we are as an institution. And the second largest unit is integrative and functional biology. When you add these together, you get our name, genomics and integrative biology. Now, basically, what does that mean? We want to use cutting-edge frontier technologies such as genomics to create technologies that encompass utility, but we also want to put it together in such a way that we develop a better understanding of the basic functions at multiple scales. These scales can run all the way from cells to organisms, and of late, even systems. And that's how we are thinking about it. The three other units that we have are chemical and systems biology. I would like to point out to all of you that while we may artificially divide science into multiple disciplines, each following its own system of teaching, problems do not know disciplines. So a problem in healthcare does not mean the solution will come from a medical school. The problem in healthcare would be solved possibly entirely by chemists. When the COVID-19 outbreak came, one of the biggest requirements was drugs. Some of the drugs were known. All that was required was a better process of making them cheaply. Now, can a medical school or even a biological lab like mine do it? No. It will be chemistry institutes. Later on, the problem could be that we don't have enough ventilators. We don't have enough oxygen. Neither a chemical institute nor a biological institute may be well equipped for that. So our National Aeronautics Laboratory, that under normal conditions makes aircrafts, came up with India's first BiPAP. Our chemical laboratory in our Institute of Petroleum came out with oxygen devices. So what you see is that while teaching has disciplines, universities have departments, problems do not obey these artificial distinctions. And that is where IGIB is part of a much larger family, the family of the Council of Scientific Industrial Research that predates independence, is one unit in a much larger system, where we try to create solutions spanning multiple disciplines. Apart from chemical systems biology, which is one of the strengths of IGIB, where we link together with multiple other CSR institutes, we also have cardiorespiratory disease biology. It comes out from our strength when we started. We started as a small unit inside the Vallabhbhai Patel Chest Institute. That's also part of our history in the Delhi University. And inside this institute, we were able to build what the foundation of what became IGIB. We got into a strong association with allergy. At one point, if you were doing allergy testing, if you were doing allergy therapy anywhere in India, it was almost guaranteed that the material that you were procuring was built at the predecessor of CSIR-IGIB. It's an area that we have stopped since as other people became competent in doing the same. And that's another important lesson that we have learned here at IGIB. People who work in scientific areas must always look at frontiers. Now, frontiers can be of two types. Frontiers can be, for example, boundaries. They can be one way of doing things versus another way of doing things. If you wanted to do diagnostics, you could do PCRs, you could do sequencing. There are two different approaches. Sometimes frontiers tend to be at the limits of knowledge. There is nothing on the other side. It's not choosing between multiple ways of doing things. It is simply choosing how far can we go. And a scientific institute must choose its frontiers. For IGIB, the frontiers could be in applications, where often you tend to know the various options in front of you. It could also be in pursuit of brand new knowledge that you have no idea what's going to come out of it, except you're reaching the limits of human knowledge. If a few simple examples will illustrate this point. When this came, one of the most important things that was required was the importance of testing. Now, how do you test? You can test using conventional qRT-PCR. IGIB, being a molecular biology institute, is very well set up for it. And we did our testing. I think we have done at least 10 to 20,000 samples have been tested at IGIB. And that is beyond the numbers we have done for internal testing for a variety of purposes. But you can also ask yourself, given our domain knowledge, can we reinvent this area? What would be limiting for India? Why are we testing at all? Sometimes you test for the patient. You test for the patient because you want the patient to have a diagnosis. That can be done on day 3, day 4, day 5. It can be done only for symptomatic people. You don't need to do it for asymptomatic people. If you only cared about that person. But SARS-CoV-2 pandemic was different. You are testing to prevent it from spreading. Now, if you want to prevent spreading, you need to test early. And it doesn't help if you test early, but the result comes 3 days later. And then you ask yourself, what are going to be the bottlenecks? If every qPCR machine is going to be 20 lakh rupees, and we need to test more than 1 million people every day because we want to test even asymptomatic people who've been exposed, at some point you need to invent better ways of doing the test. Or you need to invent, and these better ways can be in two directions. They can be cheaper, requiring much less equipment, or they can be really complicated, but you can do 10 of thousands of tests at once. And here comes the importance of knowing that science doesn't start in just de novo. You can't have the epidemic come and then you think, okay, I'm going to invent a test today. So the CRISPR technology called Feluda that IGIB has been in the news for came from years of investment by CSIR into IGIB, by IGIB into young scientists and students, Dr. Debojyoti Chakrabarti, and of course, Dr. Shavik Mehti, not as young, and young students working in their lab, inventing a new CRISPR for genome editing. But as it turned out, this invention led to a CRISPR that was so specific, it can be thought of as on and off, will bind or will not bind. And that can be used as a way to interrogate a simple PCR. And without a qPCR machine, you could develop a paper-based CRISPR diagnostic with a specificity and sensitivity comparable to qPCR. I will not spend much time on it, except that it took a huge amount of investment in the past into science, into inquiry, into asking questions before this could happen. I do not believe that a non-scientific institution would be able to invent such things. On the other extreme, using next generation sequencing, it was possible to do 10,000, 3,000 samples in one go. That also happened. So I would like to simply start by telling you all, it's important to invest into science on a continuous basis as a nation. It's important to invest into science, into young people on a continuous basis. I'm happy to see that in India, well, we have certain problems when all of you don't receive your fellowships on time, but at least we have a system by which there are national fellowships by which people can go on to pursue PhDs. People can pursue work. And this young workforce of India working at the frontiers is what we need. And we cannot limit ourselves to specific disciplines that we studied in school, things that we thought our institute is about. Today is the time of not just disciplinary, not just multidisciplinary, not just interdisciplinary. Today is the time of transdisciplinary. What does that mean? Now, what you normally do is when you go to school, you go to colleges, you undergo training in certain disciplines. You have multiple people in the same building, not necessarily talking to each other, but they're all there to solve different problems. You have multidisciplinary institutes. So once upon a time, there was probably biology and there was chemistry. Both of them work together. At some point, they start fusing together. And then you go towards inter and transdisciplinary, and that becomes new subjects. That's been one of the critical mottos of IGIB. How do we go forward? How do we bring together people of multiple disciplines? How do we put them together to specifically answer questions and problems and come out with solutions? And how do we do that in a way that is scalable and useful? And to do that, there is only one method: be open, maintain scientific temper, maintain inquiry, keep looking into what are the problems that society faces, keep pursuing science out of interest, but keep looking at whether your interests might be helpful to somebody in terms of providing them a particular solution. Translation cannot be forced. Translation must emerge spontaneously. And that is something I must say. You cannot translate what you do not understand. I think sometimes in the race for everybody wanting to do translational medicine, everybody trying to create a product, we forget science develops very often for its own sake. It develops because people want to pursue further understanding at the frontiers of knowledge. And from that come other people who will see applications of that new knowledge into actual problems. And that, my dear colleagues, is what we have tried to have as the core of IGIB. People pursuing science, people pursuing science as translation, and people trying to make sure that any solution that we develop are devised systematically in a way that we already have identified partners, stakeholders, viability, and we go together with them towards making sure that it matters. So my allotted time is more or less over. I think we are going to be waiting for Dr. Vijay Raghavan to be coming in. And I can see that we are reaching out. So Samatha, do you think we want to do any questions now while we wait for Vijay to come, or later?
We don't have any questions as of now.
Okay. So let me tell you a few more important things about COVID-19, because many of you must have been listening to what's coming out of UK yesterday. And I think you are in the right institute and the right talk to hear a little bit more about that. So newspapers today and yesterday have been talking about a new strain of COVID, that is spreading even more rapidly, a mutation at amino acid 501. And we have spent most of our time today looking at what it means for India and what we should be doing. And to some degree, this tells you about the importance of institutes like IGIB. So this is an RNA virus, right? You all know that. An RNA virus will mutate. It will mutate spontaneously. It can be made to mutate by human RNA editing enzymes. There has been some very nice work from IGIB in the last few months looking at how human RNA editors are able to create changes in viral RNA. These changes in viral RNA can lead to forced directed evolution of virus and sometimes control of the virus. This mutation that has come out of UK, interestingly, was found in what we thought were host-directed RNA editing of the SARS-CoV-2 virus a few months ago. What does that really mean? You have a virus producing its RNA all the time. You have human enzymes that are continuously editing the RNA, which basically means in a given patient, you will have multiple types of RNA sequences. Some will be mutated from the original, some will not. Some of these, if they are able to escape either the immune pressure or they're able to have some type of survival advantage, would then go on to become new viral strains, new viral mutants. Now, some of you have seen D614G in the past. The world had almost no D614G mutants at the time it came. But over a very short amount of time, it spread and has now become the dominant mutation all over the world. Now, this new mutation looks something like that. Because of a change in one residue, its ability to bind to the spike protein has changed. And it seems, from UK's experience, its fitness in able to spread the viral load in patients has become significantly higher. And that increased viral load, that increased tendency to spread has concerned the world. But thankfully, based on UK data, we know that it is not creating increased mortality. We know it's not creating increased symptomatic nature. And that is reassuring. Now, how does one know it's come to India or not? The only way to know is if you are continuously sequencing the virus in India. And that is one of the jobs given to institutes like IGIB, to maintain molecular surveillance of the virus, to ensure that every time something unusual happens, we are continuously sequencing the virus to make sure nothing has changed. We do it as a routine. We do it for cases having worse clinical outcomes. We do it for people who die unexpectedly. We do it for people who, despite being very severe, recover. We do it for people whom we think are getting reinfected. And that's in line with our mandate as a genomics institute. We were not a virology institute. We don't have a virologist, actually, to be honest. We, however, were the most suited place for the task. And the task was to maintain a surveillance on the viral genome, to see how the virus is changing, to identify early if a strain of clinical importance was to suddenly afflict India as a nation. And we found that with this program, it was not that difficult to bring partners. And to do that, we were part of a much larger team put together by the principal scientific advisor to the Government of India, Professor K. Vijay Raghavan, who very early on in this particular area was able to foresee the importance of science in fighting this pandemic and put together multiple verticals, of which one was molecular and digital surveillance, of which we played an important role. I'm very glad to see that Professor Vijay Raghavan has joined us. He is one of those names in India that needs no introduction, but I will say a few things about him that strike my mind as being very relevant to today's discussion. He trained as an engineer at IIT Kanpur. He did not train as a classical neurobiologist. He went from there into neurobiology, into aspects of neurobiology that can be called fusion between genetics. I was talking to you all about being transdisciplinary, to transcend disciplines in the search of a problem and answers to it. He, of course, all of you know, went on to be one of the people who were the initial sparks behind NCBS, becoming one of the most powerful, important scientific institutions of the country. He went on to become the Secretary of Biotechnology. During his tenure, many critical initiatives were introduced, and he has since become the principal scientific advisor to the Prime Minister, a job that in the time of COVID pandemic has come with probably levels of burden that he could not have possibly anticipated when he took upon this responsibility. But with his shoulders that look much broader than the pictures would make you think, he has been very valiantly carrying forward the battle, and we are very happy that IGIB has been a small part of that large battle. Over to you, Vijay.
Thank you very much, Anurag. It's, of course, a great pleasure and an honor to be with all of you here. One of the wonderful aspects of science is that when there is a crisis, which to people outside of science seems impossible to solve, that's what stimulates scientists more than anything else. So we tend to look upon these not only as practical challenges, which is of course very important, but we also take them in our stride as major intellectual challenges. And the reason for that is science is about looking at areas whose solutions are not obvious. If the solutions were obvious, then they're obvious. One wouldn't go ahead. So in that situation, let me very briefly, how much time do I have, Anurag?
Sorry, you have 40 minutes, Vijay? After which we move on to questions.
Do we have time for questions? If
Yes,
I cut my short? Okay.
We have time for questions after that.
Yes, yes. We have time till 5 o'clock.
Excellent, excellent. Good. Hi, Samta. Uh, so this is, a situation today which is extraordinarily unusual. And if you had asked scientists in 2019 about how science can deliver to the economy and to society, they would have classified science as basic science, applied science, science which is involved in, translation and levels of translation, which then lead to application. And this would have been a long process, in their opinion, and rightly so. And then, when asked why should countries such as India invest in science, they would answer that, oh, without investment in basic science, you can't get applications. And without those ideas coming from potential applications into technology, you won't get technology. And then the devil's advocate would say, oh, that's very good, but we have such a large number of people who need immediately the benefits of technology. Why don't we just buy those benefits? Why do we have to invest in basic science training at all? Why not just buy the benefits and then, become a rich country and then worry about basic science and technology? After all, that's what other countries, many other countries have done. They didn't invest hugely in basic science. They invested in, education and training, but not in research on a large scale until they were rich enough. And many smaller countries have done that. So this would have been the view in 2019. Come 2020, and with the onset of the pandemic, something rather extraordinary happened. Irrespective whether you are an algebraic geometer or an astrophysicist, you found ways by which, can you hear me?
Yes, we can hear you loud and clear.
Good. Yeah, good. Thank you. Because there's been a power outage here, but it looks like I'm on UPS. Okay, that's good. Okay, good. So come 20, we have an amazing situation where, algebraic geometers, astronomers, biophysicists, telecom engineers, all of them got together to do wonderful things. And this happened not just in India, but across the world. In other words, when there was a crisis and technology needed to be applied immediately, developed and applied immediately, everyone put their shoulder to the wheel. Now, this is absolutely fantastic. And, two questions arise. Why was this not easily doable earlier, if it is doable now? And secondly, how is it sustainable in the future if it is doable now? Now, these are the questions which we must answer. Let me take the second part about sustainability of doing this. I'll give you a short answer, then I'll elaborate. And then I'll answer the first question also briefly and elaborate on that also. Now, if you have an organization, and if that organization has to look at what it needs to do going ahead in the future, typically it will have about 1/3 of its resources as redundant. In other words, if you were to remove those resources at peacetime, you would argue, if you were a finance ministry person, that this is wasteful. Let me cut 1/3 of IGIB or 1/3 of this organization or that organization. No difference will be seen. Now, this is a dangerous solution because that 1/3 is what is used in a crisis like this to ramp up extraordinary solutions at high power. In other words, the redundancy which you have in a system, if it's redundancy of quality, it can rise to an emergency occasion. This is another way of talking about the value of a safety belt or an airbag, right? These are completely useless if you're not having an accident. And you'll say, what is the use of the safety belt? I mean, it's just, I've not had an accident at all, right? But that's not the way to look at a safety belt. If and when you have something unexpected, this is going to be useful, and it would be very silly to dispense with a safety belt at regular times. Now, the first point, if it could be done now, why wasn't it done earlier? And there we can't use the safety belt metaphor. There we're looking at a metaphor of a different kind. that you have basically three kinds, and pardon my mixing metaphors, but you have three kinds of trains going in three different railway tracks at peacetime. One is the train of science, who looks at reaching destinations on a time scale of years or decades. The second is the train of industry, which looks at reaching destinations in quarters or half yearly or yearly terms. And third is the demand from society and from politics, which wants results by Friday evening, right? Now, these three trains are going at very different speeds, and we are asking all of us to exchange materials between these trains so that each can benefit from the other. There's a fundamental problem here which has to be solved. But it's a solvable problem. It's a solvable problem if there are devices which we make which can interface at vehicles going at different speeds and communicate between them. Not just communicate ideas, which is easy, but communicate goods between them, which is much more complicated. So these are the two major problems facing us, which we have learned from the pandemic. Why we couldn't do things we have done now earlier, and that's because of the different speeds of different processes. I mean, there are always many things which we traditionally crib about regulation, the difficulty in doing this or difficulty in doing that. But the fact is the pressures to do something, even if they were there at peacetime, the different rates of movements of these trains become very different. Okay, and what we need to do going forward is to find ways by which the redundancy which we have in the system is used, in a proactive manner. Now let's come back to another point. And this is a point about the time scale of investment and when they pay returns. I was on a conference call which had some very distinguished people dealing with today's pandemic. Samya Swaminathan, Tony Fauci, Jeremy Farrar of the Wellcome Trust. And at the end of this, going away, Jeremy Farrar made an interesting statement, which actually shook me. He said that we must deliver to society on an instantaneous basis. And this was from the director of the Wellcome Trust. I mean, he may not have used the word instantaneous, but he wanted to look at rapid delivery of solutions. And this is from the director of the Wellcome Trust, which funds discovery, which is very long-term, right? So how does one reconcile these two things? I mean, discovery does take a long time. So let me provide a tentative answer to this puzzle of how redundancy and immediate purpose can be done. And we'll come back then to how these three different trains can be communicated with. The answer lies in similar ways between the two problems. Now, let's look at an institution, whether it's IGIB or IIT Madras or whatever. Within that institution, it has got people of different capabilities, different timelines on the way they do things, different ways in which they do things. It will have the electrical engineer and the tabla player and someone else who's your evaluation committee is constantly thinking about how to throw out because they're useless, and someone else whom your evaluation committee thinks is a genius. The mistake we have made in our institutional governance is the following. We've asked accountability at each of these individual levels, right? At the finest level of granularity of graduate student, postdoc, investigator, each of these to be accountable at a national level. How is so-and-so in your faculty or in your tech transfer area, how is that person doing? All of that is really the business of the institution. It's not the business of people outside. The people outside should be asking, how is that institution doing? And I would say not even that. I mean, that is more of an administrative issue. The people outside should be asking, how is our investment in these kinds of institutions? How is that doing, right? In other words, you don't ask how an individual in IGIB is doing. That's something which is interesting to them. You don't ask how IGIB is doing. You ask how CSR is doing. And you ask, what is the relationship between the S and the I of CSIR? Is that delivering to society? But you should not get a response, nor should you force a response where the CSIR Director General says, when I talk about chemistry, I have these labs working, and in those labs, I have these people working, and amongst those people, these are the people who have done extraordinary things. And last year, this person did this, and this year, this person did that, and this year, this lab did that. That is all your internal matter and should be your internal matter. Today, we're making a mistake of looking at all of that as accounting principles of organizations. And indeed, they will do well or okay or badly by those measures. But they're neither here nor there. Doing brilliantly on those measures doesn't serve the social aspects, and doing badly on them doesn't necessarily mean that the social aspects are not being looked at. So these are, measures which are useful for the inner functioning of the unit. So that inner functioning of the unit should be left to those who are running the inside and not be conflated with the outside unit. If then you look at the outside, there's a big challenge. How does such a unit, which inside is so diverse and has got an institutional head who's supposed to manage the inside, how is that head supposed to manage also the outside simultaneously? And there will be a very difficult charge given to that head to partition their hard drive in a manner so that they can deal with the inside on one side and the outside on the other and do it well. This is not an easy task at all. Very few individuals can do it. But if we learn from global structures, from structures in places like Barcelona, in Cambridge, in Marseille, in Boston, and in the Bay Area, institutions have developed structures full-time, dedicated with people who constantly do this all the time. So the Jet Propulsion Laboratory focuses on it's a NASA organization on one side, but it's managed by Caltech. But that doesn't mean Caltech professors sit on the board and look at it on a day-to-day basis. It's a light touch management, but it's an example of Caltech's extraordinary outreach where the inside of Caltech does pretty much what they want. But the outside, that is the JPL, does phenomenal. And we have such structures here. If you look at IIT Delhi, they've created structures for interacting. IIT Madras, IIT Bombay, the NCBS INSTEM structure has created CCAMP, CCMB has created structures. These structures should become more and more empowered and more independent of their institutions and not be seen as arms of their institutions and be adventurous to solve problems using the resources of the institution inside, but any resource. Institutions should be left free, but should have the major accountability on the long term of having the ability to answer any question at any time over a time scale of the immediate to the long term. So this is the way our institutions need to be restructured. It's happening autonomously in some ways, but it needs to be facilitated a lot by removal of regulation and also from both some kind of fire in the belly from inside. Now, let me end by saying, what are the ways by which these three different trains of communication, of movement, of science, of industry and society, how can they communicate with each other relatively rapidly? You again need interface structures to match the impedance between these different speeds of movement, and that is eminently feasible, but that requires both people and structures which are dedicated to purpose. And therefore, you need people of a mindset whose full-time goes into thinking about how academia can communicate with industry and vice versa. Indian industry has resources to solve many problems, but it is be very foolhardy of them to invest in those resources to solve those problems currently, because those problems require enormous risk And while it has capital, it doesn't have risk capital. Companies abroad, such as Google or Amazon or GE, each of them have a research budget which is more each year than the US National Science Foundation's budget. In that situation, a company in India, be it a Tata or a Mahindra or Adani or Ambani, to put in money for research would be risky in a situation where it's much easier to get technologies in various near finished forms and take it to competitive advantage. So one can exhort industry to put in money to research, but they would be careful because they don't have risk capital, they have capital. Similarly, one can exhort academia to work with industry, but you just have to look at academics, even in applied arenas such as in CSIR, and ask them, what they have to offer to industry. And most academics all over the world, including, and India is no exception, have a substantial part of their head in the sky with very little of their feet on the ground. So that what our academics suggest as TRL 6, 7, or 8, industry would see as TRL 1 or 2 or 3 or 4. That is the kind of gap which is there between our interactions. So these two systems have different challenges, different requirements. So you need another kind of structure which allows these to talk to each other and incentivize investment of industry directly in academia, because the huge amount of intellectual capability in academia, the phenomenal infrastructure we have, and the amount of land we have allows putting up of real and intellectual infrastructure dedicated to industrial interactions in our academic spaces. These are not new ideas. These are ideas which were done some years ago with difficult consequences, but these are now feasible. The time has now come. There's a greater acceptance of that kind of interaction. Similarly, an interaction between industrial success and with societal needs. Societal needs are immediate. You want quality nutrition today. You want schooling today. You want agriculture to be, cutting edge and not dependent on the vagaries of the monsoon or pests or fertilizers or whatever. So all of that needs to be addressed. Now, for that to be addressed again, you need another interface between society and industry to look at problem solving in ways which procurement by government, which is a major procurer, by state governments and all of that, allow the development of indigenous technologies to scale, building manufacturing in a collaborative manner internationally, getting international investment to allow this to do. So the problem of these trains going at different speeds can be met so that every weekend, every month, every year, you go forward if you hit the instrument of policy and regulation, because those are immediately scalable, in addition to putting investment in specific examples. So to summarize, a very, very complex problem of how we take post-COVID research ahead can be broken up into components about what we do, what industry does, what society and politics does, and how they can interact with each other. We need instruments which deal with this. And it's our responsibility as government, as leaders of institutions, as scientists to put these two together. And similarly, going ahead, in terms of our institutions having impact on potential new crises, which you don't even know what they're going to be, we need to have much more internal variability in functioning, but a self-organizing machine so that institutions and groups of institutions can serve greater positive functions on scale. These are all feasible. It requires, in my assessment, something like 5 or 10 or 20 people nationally dedicating themselves to these tasks, people of quality, young people, people who are driven, but people who are willing to put more time on these tasks than on their own career goals, which will actually be served by putting time on these tasks. So I'd like to stop here and be very happy to take questions. Thank you.
Thank you very much, Vijay. That was absolutely very useful in trying to see how science allows us to face pandemics, but with the right human behavior.
Right. Thank you so much, sir, for those illuminating words and explaining how the entire science process works and what can get better. We have few questions. The first question that we have is, now that India is taking the spotlight for manufacturing vaccines in large scale for the world, what are the logistical hurdles that you see in delivering it to the population?
Thank you. So, India has for long been a major vaccine exporter, and there have been a handful of companies which have been involved in this. And it's done so in an interesting manner, basically looking at vaccines up their manufacturing, partnering with global vaccine alliances, and partnering with philanthropic foundations and with the WHO for delivery. So this has been pretty much the route which India has taken till now. During the pandemic, India has also invested in vaccine development to scale, and now that has resulted in many vaccines which are in the pipeline, both co-developed with international companies, but also being developed here. Now, in terms of the delivery, there is a committee headed by Dr. Vinod Paul and Mr. Rajesh Bhushan, the Health Secretary, NEGVAC it's called, and that looks at vaccines procurement, the logistics of cold chain, and its delivery. India, as I said, has been a major vaccine exporter, but it's also had major immunization programs. And it's got a vaccine intelligence network, an IT backend for our vaccine delivery systems. But our delivery systems were, much smaller because they were meant for childhood immunization programs in the main, with one or two exceptions. And therefore, this new vaccine system, which is called CoWIN, is now geared towards vaccinating substantial components of our population, looking at cold chain, delivery. It will have our election system also copied to see how, in a manner similar to how we conduct elections, we can conduct this. And it will have also our digital system in place so that we know who's been vaccinated and who needs a vaccine when. So all this is, there were review meetings over the last few days, and it's pretty impressive to see how much of this has been put together. And as vaccines reach emergency use authorization over the next few weeks, we will see a rollout, which I think will be impressive and speedy.
Thank you so much for the answer. The next question I have is, India was one of the first few countries who recommended universal masking for COVID, and the office of the PSA played a huge role. So can you please tell us what was the thinking process behind this, and how the office of the PSA played a huge role in this?
Well, one of my senior most colleagues, Dr. Shalja Vaidya Gupta, pointed out, looking at the use of face coverings and masks in the Czech Republic, that it's something very important for us to do. And she got all the literature together on that, put it together, designed a manual for publicizing the use of masks and face coverings, and worked with the health ministry to get that out. There was enormous resistance the world over to the value of face coverings and masks. And fundamentally, the point is that Shalja's persistence overcome that. So that's very important to keep in mind. So kudos for that. And I must say that the Prime Minister came in and said that, look, this is silly, this is very important, this needs to be done. And that tilted the balance completely, of course, and that allowed the use of masks on large scale. That said, there was a global concern about this, which had many apparently legitimate aspects. And they stemmed from a wrong placement of values in such contexts, which I think is a very important lesson. There were two particular wrong placements of value. Three actually. One which says that masks may not be useful, right? Second, it said that if they are useful, they're useful to healthcare workers. And third, it says because they are useful to healthcare workers, having them publicly used will deplete them for healthcare workers. Now, as you can see, you don't have to be a philosopher or a logician to see why these three arguments put together are pretty messy. You're saying it's not needed, but if it's needed, I need it. And if you take it, then my need will be depleted. And this doesn't make sense. And it also doesn't make sense for certain kinds of things to do randomized controlled trials, both because they're not feasible, but also because a precautionary principle suggests that the potential gain from wearing a mask is much greater than the potential uselessness of it. And therefore, this use of masks started going globally up phenomenally. Anecdotal evidence and various other kinds of measures correlates point to their value. Laboratory experiments with aerosols and droplets point to their value. So overall, it looks like this is certainly very valuable. And as information comes in on other respiratory diseases, to see whether those have declined or stayed static will also be of value in seeing how, amongst many other components, masks may also have added value.
We have one question on YouTube that, as you said, India needs collaborative research in different subjects. But what are the steps Education Ministry is taking to promote collaborative research in various disciplines? Because most degrees are uniform throughout. So how after that, how does research suddenly become collaborative? This is the question.
Well, there are two components to this answer. One, please do take a look at the new national education policy. And that is actually being rolled out impressively at steady steps and paces. It allows undergraduates in particular, but elsewhere, others also, to take a combination of courses in multiple disciplines for their degrees. And it's a big challenge implementing that when we have created structures, colleges and institutions which are extremely specialized. How, if you go to the School of Planning and Architecture, can you take a course in music or in chemistry? Those are the kinds of flexibilities which are there. Implementing that would be a challenge. And so we're going to see more of that. It's about time. And we should see ways by which this collaborative work at the undergraduate level comes. The second component is research. 90% of our research funding goes to 10% of our institutions, the central government aided institutions. And 90% of our students go to colleges and state universities, which receive only 10% of the research funding. Now there's a hope that we'll change this soon by looking at ways to invest more in research by having centers and mentors coming in together to amplify the footprint of science, both in undergraduate contexts in colleges and in state universities. The new National Research Foundation, which is coming up, aims to serve just this purpose.
I have a last question. So this IISF theme is science for self-reliance and global welfare. So what, according to you, are some thrust areas in science India should focus on in the coming 5 or 10 years to achieve self-reliance, even after factoring in the pandemic?
Thank you. First of all, to do this in a 5-year period is an enormous challenge. I would say, or was an enormous challenge. There have been some fundamental changes in science which give you a sliver of hope of doing this really well. But to do this well, we need to first define what we mean by self-reliance. And the pandemic has pointed out how the breaking of global supply chains, which rely on a few strong nodes, can be disastrous. We have farmed out, because of lower cost, many capabilities and become an assembly and export power rather than a design, development, assembly, and export power. So there must be some areas where we are also a major node and we interact with other nodes. Now, this would seem a very difficult task for the simple reason it's not a technological problem. It's not a science problem. Because from a science and technology perspective, these are solvable. It's a problem in global economics and trade also, right? And therefore, how does one do this and be competitive? You can develop the best, testing kit or a sequencing machine by putting enough effort and care in multiple ways. But you have to compete with the big players in the market and be able to sell globally and nationally. The Indian market by itself is not sufficient. And in any case, the Indian market is open to others also. So this is a basic challenge. Now, this would have been a very difficult task because you want others who are also doing well, they will be doing better. So you can't stop that. But given the extraordinary development in the last 5 to 10 years about the value of design in manufacturing, there is a hope for India. Whether it is from semiconductors to various kinds of manufacturing, whether it's from a shoelace to a space telescope, design is the key. Good design, really high quality computer-aided design, where every component is factored into materials, what it does, where it is, and so on, is the key. This is something where young people can excel and grab a global market. So pushing R&D into a situation where design as an exportable commodity, high quality, high-end design, allows us to combine that with manufacturing, which again has become localized, to export a combination of calibrated high quality manufacturing in chosen areas. And there are many areas where we can do well. Semiconductor design is a good example. Qualcomm is one of the largest non-fab semiconductor companies. It doesn't have manufacturing. It has design, and some of its top design labs are based in Hyderabad and Bangalore. So, we can surely have ways by which our scientists, our entrepreneurs can take on these kinds of areas. That requires a concerted effort and not merely a statement of that opportunity.
Thank you, Dr. Vijay, for such an enlightening talk. And thank you for answering all the questions. So after this, now we have a video that highlights IGIB's research. So please do watch.
Thank you very much. Please, I will.
The CSIR Institute of Genomics and
So
Integrative
that video
Biology
was on live.
is one of the constituent labs of the Council on Scientific Industrial Research, India.
That will be visible on YouTube.
It started
right,
as a
Not
biochemistry
yet.
lab
I think.
trying to produce
I
biochemicals,
think we can.
but was organized very soon
Yes,
to meet India's need.
Thank you very much. Take care. Bye-bye.
Its
Bye-bye.
mandates to take concepts
Bye-bye.
in emerging
Thank
technologies
you very much.
such as genomics and translate them into applications and
Okay.
utilities
So,
that are viable for the people of India. I am proud to say
so good.
that over 2 decades of
Watch the
efforts
video. I guess I need
in
to
the
go to
field of
YouTube, right?
genomics, CSIR-IGIB
Yes, sir.
Okay. All right.
across India. We have what are called decision units, unlike departments. One of the foremost is genomics and molecular medicine. In that, we've been catering primarily to rare genetic disorders. India is a very interesting case of diversity and yet lack of diversity because of a number of societal practices that have taken place over the last 2000 years. Because of our rich history, we have people of every possible genetic background, starting from what appear to be ancestral Indians, periodic minglement with people coming from the European side, offspring of original migration going towards China, and people have been mixing with us throughout our history. But because of strict marriage practices, many of these communities within India are also highly inbred. So in some ways, we have the equivalent of multiple, very, very distinct genetic communities, but very different from each other when you take the entire span of India. Using this as a starting point, IGIB has focused on characterizing the Indian genome, starting from the first human genome sequencing that happened in the country. A series of projects designed for better understanding of what shapes our health as Indians and how we can make it better has followed. It has spilled over from pure genomics into proteomics, metabolomics, physiomics, in fact, integrative omics. Towards this, we have certain disease focus areas that we also work extensively in. Neurogenetics is possibly one of the strongest areas of CSIR-IGIB, but in terms of general diseases, we also do substantial work in cardiorespiratory disorders. Within cardiorespiratory, we focus on one of the main problems of Indians, which is diabetes, ischemic heart disease. We also focus on lung diseases. India has much more than expected chronic obstructive pulmonary disease, given it's a relatively young nation. We already have amongst the highest burden globally, and we do a substantial amount of work in trying to understand why Indians have amongst the worst lung functions in the world and why is respiratory health of Indians poor. Many of the concepts that we work on are closely intertwined by cardiometabolic diseases, starting from diabetes to vascular disease, and that's been a major area of work. As our name indicates, integrative biology, putting everything together in a way that makes sense, is absolutely critical to what we do. And we have a decision unit towards functional and integrative biology, focusing on cellular or tissue architecture level understanding of what truly happens. Chemical and synthetic biology are other key areas. You cannot really build products, diagnostics. You cannot invent new ways of doing things without a good interface between biology and chemistry. And that has been a core effort of our institute, evidenced recently by a test that we called Feluda, bringing together our understanding of genetic nature of diseases, our understanding of sequencing, our development of new enzymes of the class of what's called CRISPRs, and building of platform technology to convert that into diagnostics. The last but not the least decision unit is big data. I'm sure you can all imagine that the type of efforts IGIB is leading generate massive amounts of data. Using such data well is challenging, and big data analytics is possibly one of the most active areas in the country. In particular, IGIB has focused on building an interface between biomedical and data science, and informatics at a molecular biology, cell biology level is just one facet of that. We are moving more and more towards integration of newer, let's call them solutions, such as artificial intelligence, into this very complex area. And our vision is that India would become progressively a data-rich, data-enabled nation. Today, we are people poor, well, we are people rich, but data poor. We hope to be very soon, given important initiatives by the government, such as the National Digital Health Mission, of becoming both people rich and data rich. And towards that, we are trying to build the interface between AI and health. IGIB plays a prominent role, not only in working on these areas itself, but on building consortia with other leading institutes, whether biological, medical, or computational. And we look forward to playing a key role in taking all these important areas forward in a holistic way towards making India a scientifically stronger and prosperous nation.
The virus, which originated from the city of Wuhan, has now engulfed the whole world within a few months. Millions have lost their lives in this pandemic, and the countries are bearing the brunt of economic loss due to the lockdown. On the other hand, various efforts are underway on war footing to tackle the challenges posed by the pandemic, like rapid diagnostic kits and attempts to develop a suitable vaccine for the infection.
We are very happy to know that the cellular technology, which was developed at CSIR-IGIB and was licensed to Tata Sons, has now been approved by DCGI and is slated to be scaled up for market release very, very soon. It was work that was done over actually an extended period of work done over almost 2 years, where we were trying to detect single nucleotide polymorphisms responsible for sickle cell anemia under the PM monitored project sickle cell anemia mission. And then at the beginning of the pandemic, we repurposed this for COVID-19 detection. It uses cutting edge CRISPR-Cas9 technology. And it has been a lot of hard work put by my colleague Dr. Shobik Maiti and a lot of students during the entire pandemic period. And now the market success, or the success in the hands of the people or the users, would really be what we are looking for at this point of time. So it uses the CRISPR-based technology, which will be able to detect the presence of the COVID-19 nucleotide sequence or the virus. It will be as sensitive and specific as the qPCR, the quantitative real-time PCR gold standard test, but will not require expensive instrumentation. It will be way cheaper, and also it would not require to it. So which means that one can actually do this test at a relatively point of care kind of settings.
In India, various laboratories of Council of Scientific and Industrial Research are also working on genome sequencing of the novel coronavirus. One of them is Delhi-based Institute of Genomics and Integrative Biology. Scientists have been working diligently on RNA genome sequencing of the virus, and they have been successful in completing the genome sequencing of various samples.
So all these COVID genomes have a 30,000 Legos put together. Now how do they arrange those 30,000 blocks is something which makes them unique, makes them identify into different lineages and different strains. So the first thing which we did was, which was initiated mainly by the dynamic leadership of our director, Dr. Raghavan, wherein he got in touch with NCDC, and NCDC has been our partner, a very proactive partner in this regard, wherein they are happy to share positive samples RNA and which we use for sequencing. So that's kind of a broad protocol where we receive RNA from NCDC, we convert it into double stranded cDNA, we do amplicon PCR to convert it into targeted amplicons from COVID genome, and then we make libraries and then we put it through Oxford Nanopore for sequencing. And on the parallel front, what we are also doing using Oxford Nanopore is working towards a protocol which can be taken to a field if required as well. So as we saw in the lab as well, that the machine which we are using at the moment is pretty much we can keep in a pocket and go, with a very small portable computer attached to it, which can also do sequencing while we are driving in a car. So we are also working towards a technology development where sequencing can be taken to the site where it is required. If we want to move into a domain of designing drugs and vaccine development, the sequence of the viral genome will be important to know that what part of the genome, for example, is consistent across viruses which may be targeted by drugs, which can also be taken forward for vaccine development, and this will all, and that all sort of layered information we will get through the genome sequencing as well as the genomic surveillance, that what is the spread and the footprint of the virus across the geographical expanse of India, and how it is that how is the geographical expanse of the virus is linked with the genetic uniqueness of the virus, which we are looking into at the moment.
In 2015, Mohammad Nazir, a 44-year-old sweet seller from Agra, petitioned the President of India. He was requesting permission for 6 of his 8 children to be euthanized. By the age of 2, the children were afflicted by a crippling neurological disease that resulted in seizures, limited movement, muscular dystrophy, and impaired growth. Doctors couldn't diagnose the condition, and Nazir was desperate to end their suffering. The family's plight caught the attention of K.V. Shamsuddin, who studies rare diseases as part of a project called Guardian at the CSIR's Institute of Genomics and Integrative Biology. The mystery disease fascinated CSIR's resident scientists Sridhar Sivasubbu and Vinod Skaria, India's leading experts on genomics. The team then embarked on a 2-year-long quest to find the solution to the puzzle.
And we contacted back the family and we informed them so we can help them regarding the diagnosis of this disorder by using genomics approaches. So the family sort of agreed. The very next day we got another call from one of the NGO, that is Human Welfare Foundation, informed us by saying that they can assist all the medical, they have all the medical team along with them. So any requirement from their part, they can do it. We have discussed this case with Dr. Shafali Gulati, and she agreed to take this family or see this family.
Using whole exome sequencing, a technique which analyzes the protein coding region of the human genome for genetic variations, the cause of the disease was determined. A single gene mutation was the root of all the problems affecting Nazir's children. The human genome contains the chromosomes which carry the genes comprising the DNA. A genome has around 3.1 billion DNA base pairs, and there are 20,000 odd protein coding genes. These are carried on the 22 pairs of chromosomes, along with 23 being the sex chromosome. A genetic mutation causes vital proteins to be absent or formed in ways that are harmful. While most diseases are caused by several genes going awry, some are the result of a single aberrant one. Nazir and his wife Tabassum were both carriers of a mutation on the MLC1 gene on chromosome 21. However, it did not affect them, as the mutation existed in only one of the copies of the chromosome. Thus, there was a 1 in 4 chance that their children could get the mutation in both the copies of the chromosome. The scientists had discovered a new mutation, the Nalband mutation. 6 of his children had a pair of this defective gene.
Present mutation was not present in any one of the Indian population previously. We went back and searched the history of the family. So they belongs to a Nalband community, and we figured it out that this Nalband community actually originated from Iran, and they migrated along with Mughal dynasty, and they spread across Pakistan, Sindh, and certain part of Haryana, and predominantly they are based on Agra and Aligarh.
Now the question was, why were so many of Nazir's children affected?
Both the parents are having one defective copy each. So we hypothesized that in this entire community it could be present. So we went back to the community and we convinced the family by saying that it could be possible that there will be more families in the community.
Over 2 years, Shamsuddin visited Agra with Human Welfare Foundation workers and knocked on several doors in Nazir's neighborhood. After giving crash courses in genetics, he would ask residents for blood samples.
Once we got these samples, and we reconstructed the family pedigree, and we found that all these affected members are closely related.
Nazir and Tabassum are cousins. Endogamy, or marrying within the community, is a practice across various parts of India. 82 members of the community who live within half a kilometer of Nazir's family have the mutation. So far, the team has found that nearly 28% of the community carries the defective gene. Social and cultural practices might be difficult to change, but the team at Guardian has now made it easy to identify the Nalband mutation.
So I said, the Guardian was a discovery phase. So we discovered a new mutation. There's a second program within IISF which started a year ago, which is called the GoMed. Okay? It is called Genomics for Enabling Medical Decisions.
Okay.
So
where the single tests are
we transfer the single test to them.
Okay.
Now this community is on an average about 5,000 members. And for now going back and doing the 82 families, it is just maybe a 500 rupees to 1,000 rupee test per individual. So you're not spending a lakh rupee
anymore.
We formed the consulting clinician. It was Dr. Shifali Gulati from AIIMS. She said that all our clinical finding is actually matching with the genetic diagnosis that you have made. Then straight away we are going to start prophylactic drugs. So once they started this drug, after almost 2.5 months, the father called me back by saying that you have a happy news, where the youngest child Aban started going to school. And next month again he called me by saying that one more child started going to school. At present there is no cure for MLC1, but there are a lot of research is going around for this disorder around the globe. So there are many groups working on this particular disorder. So in future we can expect. There was a time when this family wanted, the patriarch in this family wanted 6 of his children to be euthanized. But those days are gone. His children are not going to be free from this disease, but the genomic knowledge has gone in some way to ensure that he might probably instruct his children better, or he might have some influence in dictating the way the family will manage their future better.
इस समय हम IGIB की जीन एडिटिंग स्टेम सेल प्रयोगशाला में हैं, जहां नवीनतम क्रिस्पर तकनीक के जरिए जीनोम एडिटिंग की प्रक्रिया को अंजाम दिया जाता है। अनुवांशिक या अन्य कारणों से डीएनए में जब कोई ऐसी खामी आ जाती है जिससे बीमारियां हो सकती हैं, तो कोशिका के अंदर जाकर उस डीएनए में कुछ बदलाव करने की कोशिश की जाती है। इसी प्रक्रिया को जीन एडिटिंग कहते हैं, और जिस तकनीक से ये एडिटिंग की जाती है वो क्रिस्पर तकनीक कहलाती है।
मानिए कि कोई सिकल सेल एनीमिया हुआ है जिसको, तो उसका खून लेके हम उसी बंदे का हम स्टेम सेल बना सकते हैं, इंड्यूस्ड प्लूरिपोटेंट स्टेम सेल बना सकते हैं। तो वो सब काम यहाँ पे होता है। ये एकदम सेपरेटली रखा हुआ है। यहाँ पे हम लोग वो पर्सन का खून से स्टेम सेल यहाँ पे बना सकते हैं। और जो चीज़ हम यहाँ पे करते हैं कि वो सेल्स में हम क्रिस्पर कंपोनेंट से जीनोम एडिटिंग भी करते हैं, यानी कि उसमें अगर कोई म्यूटेशन है तो वो म्यूटेशन को हम करेक्ट करते हैं। और जब करेक्ट करते हैं तो जिस सेल में वो म्यूटेशन करेक्शन हुआ है उसको हम इस रूम में आके उसको हम बोलते हैं सॉर्टिंग कर सकते हैं, यानी कि उसको एक एक सेल निकाल सकते हैं। तो यहाँ पे वो सब काम होता है। और फिर हम वही सेल्स को हम ग्रो करते हैं ताकि वो इनफ नंबर्स हो कि वो अगर माउस में हमें उसको इन्फ्यूज करना है या कुछ और करना है तो वो सब चीज़ें कर सकते हैं। एट द सेम टाइम हम बेसिक बायोलॉजी ऑफ क्रिस्पर में भी काफ़ी काम करते हैं। जैसे यहाँ पे हम ये डिटरमाइन कर सकते हैं कि ये एक सीक्वेंसिंग मशीन है। यहाँ पे हम ये डिटरमाइन कर सकते हैं कि जो हमने जीनोम एडिटिंग किया है वो कितना सक्सेसफुल हुआ है।
ये देश के प्रमुख जीन एडिटिंग लैब्स में से एक है जो क्रिस्पर तकनीक के क्षेत्र में काम करती है, और इसके जरिए जेनेटिक बीमारियों का निदान और उपचार खोजा जा रहा है।
और हमारा लैब स्पेशलाइज करता है कुछ एक नया क्रिस्पर टेक्नोलॉजी बोल सकते हैं, एक एंजाइम जो हमने यहाँ पे काफ़ी सारा उस पर शोध किया है, वो उसको लेके जीनोम एडिटिंग करने में। तो जो बीमारियों को हम मेनली फोकस कर रहे हैं ठीक करने के लिए वो है सिकल सेल एनीमिया, जो एक खून का बीमारी है और उस बीमारी का एक जेनेटिक बेसिस भी है।
सिकल सेल एनीमिया पर शोध में लैब जल्द ही क्लिनिकल ट्रायल में जा सकता है।
जो हम ऑफ टारगेटिंग बोलते हैं, जैसे यानी कि हम किसी टारगेट को ठीक करने के चक्कर में हम किसी और जगह पे जाके अगर डीएनए को काटे, वो अच्छा नहीं होता है, तो वो एक लिमिटेशन है। तो शायद हो सकता है कि हमारा कैसनाइन वो लिमिटेशन को कम कर सकते हैं और थेरेपी के लिए बहुत उचित हो सकता है। तो ये हमारा सबसे बड़ा अभी जो फाइंडिंग है, और हम कोशिश कर रहे हैं कि इसको जितना जल्द से जल्द हो सके इसको लेके क्लिनिक में कैसे हम पहुंचा सके ताकि लोगों का उपकार।
वैज्ञानिक जिनोमिकी प्रयोगशाला है जहां आयुर्वेद की प्राचीन पद्धति का आधुनिक जिनोमिक्स के साथ समन्वय कर व्यक्ति परक और सटीक निदान इजाद किया जा रहा है। इस विधा को आयुर जिनोमिक्स नाम दिया गया।
तो जिनोमिक्स मेनली एक लेबोरेटरी बेस्ड, इन्वेस्टिगेशन बेस्ड और उस तरीके से व्यक्तिपरक चिकित्सा की तरफ आगे बढ़ रहा है। आयुर्वेद ये मेनली क्लिनिकल मेथड्स के आधार पे व्यक्तिपरक चिकित्सा है। तो आयुर्जिनोमिक्स में हमारा अध्ययन ये है कि इन दोनों पद्धतियों का मेल करवा के क्या हम बेटर तरीके से प्रिसीजन मेडिसिन की तरफ या एकदम प्रिसाइज डायग्नोसिस और उसके लिए प्रिसाइज थेरेप्यूटिक्स के प्रति आगे बढ़ सकते हैं।
आयुर्जिनोमिक्स में आयुर्वेद के त्रिदोष के मौलिक सिद्धांत और जीन या प्रोटीन के जरिए आधुनिक जीव विज्ञान की मूलभूत समझ के बीच के संबंध को लोगों की प्रकृति के अनुसार वर्गीकृत किया जाता है और ये पता लगाया जाता है कि लोगों में वात, पित्त और कफ का क्या अनुपात है और अगर ये अलग अलग है तो इसके जेनेटिक्स, मॉलिक्यूलर या बायोकेमिकल भाषा में क्या मायने हैं। इस लैब से ऐसा ही एक शोध प्रकाशित हो चुका है जिसमें मैदान और ऊंचे स्थान पर रहने वाले अलग अलग प्रकृति के लोगों में ऑक्सीजन सेंसिंग से संबंधित जीन, उसके एक्सप्रेशन पैटर्न और उनमें जेनेटिक वेरिएशन की पहचान की गई है।
तो ये पहले तो हमने ये मार्कर डिस्कवर किया प्रकृति के जरिए और उसको वैलिडेट किया इन दोनों तरह के पॉपुलेशन में, और उसके अलावा इससे ये साबित होता है कि इस मेथड से हम प्रेडिक्टिव और प्रिवेंटिव मार्कर्स, जो प्रेडिक्टिव मार्कर्स ढूंढ सकते हैं जिसके जरिए आप पर्सनलाइज प्रिवेंशंस एडवोकेट कर सकते हैं। सो वैलिडेट तो ये हो ही गया कि वात पित्त कफ प्रकृति का मॉलिक्यूलर कोरिलेट है, बट एट द सेम टाइम इसमें एक डिस्कवरी भी हो गई कि ये जेनेटिक मार्कर एक्चुअली रिस्पॉन्सिबल है हाई ऑल्टीट्यूड के अडेप्टेशन के लिए।
आयुर्जिनोमिक्स में फिनोटाइपिंग लैब बहुत महत्वपूर्ण है। अभी तक देश के अलग अलग भौगोलिक क्षेत्रों से 20,000 लोगों का प्रकृति परीक्षण किया गया है। आयुर्जिनोमिक्स अनुसंधान में भी आधुनिक चिकित्सा प्रणाली की तरह मशीनें इस्तेमाल की जाती हैं, जैसे मॉइस्चर मीटर, स्किन ग्लॉस मीटर, वेपोमीटर, हार्ट रेट वेरिएबिलिटी स्पाइरोमेट्री। क्रिस्पर तकनीक के अलावा एक अन्य अति आधुनिक तकनीक पर IGIB में तेजी से काम हो रहा है और वो है आर्टिफिशियल इंटेलिजेंस यानी AI। हाल ही में एक प्रयोग शुरू किया गया कि ब्रेन सिटी स्कैन को कंप्यूटर द्वारा कैसे पढ़ा जाए।
इसमें हम क्या करते हैं, बहुत सारा 7 लाख 8 लाख रेडियोलॉजिकल इमेज, सिटी स्कैन इमेज, ब्रेन का सिटी स्कैन इमेज हमने पहले सिस्टम को दिया, कंप्यूटर को, और वहाँ पे डीप लर्निंग द्वारा एक कर्नल बनाया जो समझ सके कि ब्रेन के अंदर कहाँ पे ब्लीडिंग है। इंट्राक्रैनियल हेमोरेज कहते हैं इसको, ICH। ये मॉडल एक बार ट्रेन हो जाता है, फिर हम उसको प्रयोग में डालते हैं और डॉक्टर लोगों को बताते हैं कि आप अपना रेडियोलॉजी इमेज, सिटी स्कैन इमेज को इसमें अपलोड करिए, उसके बाद प्रेडिक्ट करिए। प्रेडिक्ट करने के बाद जैसे यहाँ पे आप देख पा रहे हैं, ये आउटपुट ऐसा आएगा जहाँ पे ये ग्रीन मतलब यहाँ पे कोई ब्लीडिंग नहीं है, जहाँ ये रेड मतलब ब्लीडिंग है और क्या प्रोबेबिलिटी है ब्लीडिंग का।
AI का ये प्रयोग सफल रहा तो देश में रेडियोलॉजिस्ट की कमी की समस्या से काफी हद तक निपटा जा सकता है। हालांकि AI रेडियोलॉजिस्ट की मदद करेगा, न कि उनकी जगह लेगा।
मिडनाइट में रोड में कहीं पे एक्सीडेंट होता है, पेशेंट जाता है हॉस्पिटल में, वहाँ पे सीटी स्कैन पढ़ लिया जाता है, तब रेडियोलॉजिस्ट हो ना हो ये वाला सॉफ्टवेयर वहाँ पे इमीडिएटली प्रयोग में आएगा और ये बताएगा कि हाँ देयर इज ए ब्लीड, रेडियोलॉजिस्ट शुड बी कॉल्ड। रेडियोलॉजिस्ट आके फिर इसके ऊपर दोबारा देखेंगे और बोलेंगे कि सच में वहाँ पे ब्लीडिंग मिला या नहीं मिला।
ये प्रयोग अब रेडियोलॉजिस्ट के पास जाने के लिए बिल्कुल तैयार है, जहां वास्तविक उपयोगकर्ताओं के बीच इसे स्वीकृति मिलेगी। अगले 1 से 2 सालों में एआई रेडियोलॉजिस्ट की मदद के लिए अस्पतालों और क्लिनिक्स में तैनात हो सकेगी।
विज्ञान और तकनीक के क्षेत्र में आज भारत पूरे विश्व में अपनी सफलता का परचम लहरा रहा है और इस सफलता में अहम भूमिका निभाई है वैज्ञानिक, डॉक्टर, शोधकर्ताओं व हमारे देश के छात्र और छात्राओं ने। इसलिए 2015 से 2019 भारतीय अंतर्राष्ट्रीय विज्ञान महोत्सव की लगातार सफलताओं के बाद अब छठा इंडिया इंटरनेशनल साइंस फेस्टिवल 22 से 25 दिसंबर 2020 तक आयोजित किया जा रहा है। कोरोना महामारी के कारण इस वर्ष ये महोत्सव आभासी रूप व ऑनलाइन माध्यम से आयोजित किया जाएगा। ये महोत्सव विज्ञान संचारकों, वैज्ञानिकों, डॉक्टरों, शोधकर्ताओं और छात्रों को एक दूसरे के साथ बातचीत करने और जुड़ने के लिए एक बड़ा मंच माना जाता है। विज्ञान और प्रौद्योगिकी की बढ़ती मांग के कारण इस वर्ष इस महोत्सव का विषय सेल्फ रिलायंस और वैश्विक कल्याण के लिए विज्ञान रखा गया है। यहाँ छात्राओं को विज्ञान और प्रौद्योगिकी के नए मोर्चे के साथ साथ कई अन्य वैज्ञानिक विचारों को उत्तेजित करने वाले विचारों का पता लगाने का मौका मिलेगा। कई प्रतिष्ठित वैज्ञानिक, डॉक्टर और शोधकर्ता कोविड-19 वैज्ञानिक नवाचारों और विज्ञान के विभिन्न क्षेत्रों के अनुप्रयोगों के संदर्भ में अपने ज्ञान और विशेषज्ञता को भी साझा करेंगे। वैज्ञानिक नवीनता और चुनौतियों के साथ प्रतिभागियों को आमने सामने लाने के महत्व को समझते हुए इस महोत्सव में नैनो खगोल विज्ञान, आयुर्वेद और योग, अंतरिक्ष खगोल विज्ञान, खगोल भौतिकी, चिकित्सा, क्वांटम भौतिकी और पर्यावरण प्रदूषण व जलवायु परिवर्तन सहित विभिन्न वैज्ञानिक डोमेन, कृत्रिम बुद्धिमत्ता और संक्रामक रोग जैसे विषयों को भी शामिल किया गया है। विभिन्न मंत्रालयों, विभागों और वैज्ञानिक औद्योगिक अनुसंधान परिषद यानी CSIR द्वारा प्रायोजित ये महोत्सव वैज्ञानिक नेताओं, छात्रों और आम जनता को विज्ञान और प्रौद्योगिकी में उपलब्धियों, खोजों और नवाचारों में शामिल होने के लिए 9 से 12 कक्षाओं के छात्राओं की भागीदारी के लिए आमंत्रित करता है। तो आइए 15 दिसंबर 2020 से पहले इस महोत्सव में रजिस्ट्रेशन करवा के इसका हिस्सा बने और खुद को वर्तमान वैज्ञानिक ज्ञान से परिचित करवाएं।
It was indeed a nice evening with talks from Dr. Anurag and Professor Vijay Raghavan and a glance at IGIB's work. I take this opportunity to express heartfelt gratitude to Professor Vijay Raghavan for carving out time from his very busy schedule, which is definitely not at all being held by an ongoing pandemic. I'm sure his words provided everyone involved in scientific endeavors encouragement and vigor. I would like to thank Director IGIB Dr. Anurag Agarwal for his involvement and the time he has put in to make this session of Vigyan Yatra possible. Thank you, sir. IISF 2020 is being hosted by CSIR I thank everyone in the CSIR family who are deeply involved in this endeavor. I also thank the organizing committee of IISF who provided the necessary support for this session. I take this opportunity to thank Dr. Malvika Datta, Dr. Shravanti Rampalli, and Dr. Mary Eka for coordinating ISF events from IGIB. I thank Dr. Purti Katpalia, who is the outreach in charge of IGIB, and Vignesh Sentivel for helping me out today. Most of all, I thank everyone who joined this session, and hopefully everyone feels more invigorated towards building a self-reliant India built on science. Do join ISF 2020 from tomorrow. Jai Hind, good evening and goodbye.